Good morning, class, and welcome to this lesson on Geometric Optics 6, Refraction and Snell's Law. Today we will be able to define refraction and Snell's Law. A simple objective, okay? It's just defining what these things are and giving some examples of each, okay? So refraction. Refraction is the change in direction of a wave due to a change in its transmission medium. So that sounds kind of fancy, right? Refraction is the change in direction of a wave due to a change in its transmission medium. So what it means is that change in direction of a wave, light will bend, light will bend when going from one medium to another. Okay? Light will bend when going from one medium to another. That would be layman's term for this definition right here. And so here is a picture of refraction. So far, we've talked about reflection, right? Or the bouncing of a light wave, Well, refraction is like reflection, but it's just the change in direction of a wave slightly. So when a light wave hits a surface, so we'll say we're going from air to water, we have the incident ray, it hits the surface. Part of the ray, will be reflected. Part will be reflected. Okay, so part of the ray will be reflected just like a mirror. And you can probably guess that, like, for example, when you look at the water, there's glare coming off the water because you're getting some of the reflection of light coming off the water. However, most of the light will actually be refracted. So it's going to hit the water, and instead of continuing down this straight path like this, it's going to bend. Light will bend because it's going from one medium, air, to another medium, water. So it's going to hit the water and bend downward like that. Okay, so that's essentially what refraction is. It is the bending of light through a medium. And so the best example I can give to you of this, just to kind of give you something to hold on to, it's just an analogy, okay, so it's not 100% true. But imagine you have two wheels attached to an axle, okay? Not attached to a car, not attached to an axle, not attached to anything. And these two wheels are going from cement to grass. As you can imagine, as they're rolling, they're going to go slower on grass, not on cement, okay? So these wheels are going to hit the grass, and when they hit the grass at an angle, you can see this left-hand wheel is going to hit the grass first. So this left-hand wheel is going to slow down a bit before the right-hand wheel. So when this left-hand wheel slows down, the right-hand wheel is going to catch up. It's going to catch up, and when it hits the grass, it'll continue to go straight again. And so as you can see, because this one slowed down before this one, it changed direction. Okay, so that's just an analogy to give you an example. Okay, so refraction. Refraction, we have something called a refractive index. We have a refractive index, and we define that as n. Oh, that's bad. N. Okay, and this refractive index equals the speed of light in a vacuum, or c, over the speed, the velocity in the medium. Because what we're trying to tell you here, I need to fix that. The velocity in a medium is going to be slower than in a vacuum. Okay, speed of light in a vacuum is 3.0 times 10 to the 8th meters per second. But when it's going to be in a medium, it's going to go a little bit slower. Imagine running through air versus running through water. If you're running through water, you're going to go a little bit slower. Okay, so we have a refractive index. So light will go different speeds or velocities, different speeds in different mediums. Nothing that we can tell with the naked eye, but it does go different speeds in different mediums. And so we have refractive indexes, okay? And so for example, if it's going through ice, the refractive index is 1.3, meaning the speed of light in a vacuum is 1.3 times greater than the speed of light in ice. Okay, so that's just an example. So this is going to be n. N is equal to the speed of light in a vacuum over the speed of light in a medium. Okay. So very, very common test question and very common thing to understand is what's changing here. Well, we know that when refraction occurs, velocity changes. Velocity changes. It's going slower or faster depending on the medium. So velocity changes. What about frequency and wavelength? Well, V equals lambda times F. So if this changes, that means one of these two has to change as well, or both. Okay? And what we find here is in different mediums, wavelength changes, frequency doesn't. Wavelength changes, frequency doesn't. Okay? The best analogy, this is going to be just another analogy again. Imagine I have two rivers. Okay? Rivers. This one's fast. This one's slow. And let's say we're dropping stones in the river at a constant pace. I'm dropping one stone in the river every second. Okay? So as I drop the stones, it's going to cause a ripple. And in the fast river, the ripples are going to be very far apart. And we would call this the wavelength, okay, from crest to crest, so to speak. In the slow river, I'm still dropping the stone at 1 stone per second, but because the river is moving slowly, the ripples are going to be a little bit closer together. So the wavelength decreases. So notice, faster speed, in the faster flowing river, faster velocity, we have a bigger wavelength. In the slower flowing river, we have a smaller wavelength. But the reality was for both, my frequency was 1 hertz because I was doing 1 stone per second. So frequency doesn't change, lambda does change, and that's just meant to be an analogy to give you something to hold on to when asked this kind of question, what's changing? Because it probably will be asked. So we have Snell's law of refraction. Pretty simple. When light, here two rules. When light goes from medium 1 to medium 2, from medium 1 to medium 2, from a refractive index, N1 is smaller than N2. So for example, in this picture right here, N1 is, the refractive index in air is 1, the refractive index in water is 1.3. So N1 is less than N2. It's going from air to water, N1 is less than N2. The rule is light will bend toward the normal. Light will bend toward the normal. So light will hit and bend toward the normal. You can see this is the normal line right here. And this angle is going to be smaller than this angle right here. It's bending towards the normal. Okay? And when light travels from medium 1 to medium 2, and N1 is greater than N2, so going the opposite direction, light will bend away from the normal, away from the normal. So as you can see here, light's going from water to air. It's going from a greater index of refraction to a smaller index of refraction. This is the normal, and it was coming at this angle, and it bent away from the normal. It bent away from the normal, okay? One thing I want to point out, I'm going to just write it real big here, away from the normal, okay? I notice a lot of students have trouble with this concept of the normal because in most math classes, when we start measuring angles in geometry or whatever, we measure angles away from the horizontal like this almost all the time. Even in this class, in mechanics, we always tend to measure away from the horizontal, okay? And so it's very common for people to write in the angle away from the horizontal and measure this angle right here. But look at all these angles that we're looking at in these pictures. It's always the angle away from the normal or from the vertical line. And it's not a hard thing to change. It's just something you're not used to. And because of practice and practice and practice in math classes, we tend to write this angle as opposed to this angle, and then it messes up all of our math. Okay? So just be aware of that. It's going to be away from the normal and not from the horizontal. Okay? So, we have Snell's law, which is a mathematical equation, which is going to be N1 sine theta equals N2 sine theta. we have, oh, sine theta 1, sine theta 2. So in this example, this would be theta 1, this would be n1, this would be theta 2, this would be n2. Okay, so if we know the indices of refraction and or one of the angles, we can calculate the other angle, or vice versa. Okay, so simple equation. It's just a matter of plugging in the correct number in the correct spot. Make sure that your ones are together and your twos are together, because those are easy to get mixed up as well. Okay, and I want to point out another test taking strategy. Whenever a lot of times they might give you a shape like a triangle, and it's going to ask you which way is the light going to bend. And so let's say the light's coming like this. Okay, draw the normal line on every single surface. Okay, so in this example here, if it was going from air to glass, okay, this is glass, and the light was coming this way, it would bend towards the normal. So let's say it would bend like this. Okay, so we're going straight across now. And then when it goes from glass to air, it's going to bend away from the normal. And so when it hits this point right here, it's going to go away from the normal. So this is just one example of how light will bend when it hits glass. So the normal is not always up and down. It can be any direction. And so the best thing you can do is draw the normal line to the surface, and that will help you out a lot. Don't assume the normal is in one direction. Okay? So we have one last thing to cover, apparent depth. This idea of refraction is the reason why things in water, for example, are not where they appear. You might have seen a penny or something in water, or like an object you were trying to reach for, maybe a fish, and you stuck your hand in water and it wasn't there, and you could have swore it was right there. But the reason is, like in this example, let's say there's a treasure chest at the bottom of the ocean here. Okay, cool. The treasure chest is right here, and the light from the treasure chest is going to hit the observer's eyes. And as the light travels up, it's going to hit the water, and because it's going from water to air, it's going to bend. It's going to bend. And this bending of light makes it appear like it's coming from right here. This is why when you're looking at anything in water or a different material, it's not always correct. It looks different than what it really is. And so we have an apparent depth. It appears to be right here, but it's actually right here. Okay? And so we have an equation for this. D prime is equal to D over N2, or times N2 over N1. And D prime is apparent depth, and D here is actual depth. Okay, apparent depth and actual depth. Okay, simple equation again, you just have to know how to use it, okay? And just as a side note before I finish, this is the reason, refraction is the reason why if you put a straw in water it appears bent, or if it appears broken, because the light is refracting, it is bending away from the normal. And also a fascinating thing here, we look at like Coke in a bottle, like liquid in a bottle, or like a root beer in a mug or something, and it always appears very full. It appears to be full right to the very edge. That's because we're looking at the liquid inside glass, and we're looking from air to glass. The reality is because light is refracting in the glass, the mug actually appears much more full than it really is. And so if you look at this picture right here, it's a Coke bottle inside a glass. So there's no refraction there. It's glass inside glass. And so looking at it, you can actually see how full the Coke bottle is. And when you look at it, you feel almost kind of cheated. Like, wait a minute, I'm only getting that much liquid. But the reason it appears full is because of refraction. But in reality, it's only so full. So just a cool little thing to share with you.